Good morning, everyone. I'll be talking today about the implementation and performance of SONiC Dash on Intel IPU. Here's a quick outline, just a quick overview of SONiC Dash for smart switches, introduction to Intel IPU. I'll just briefly talk about the features and the scale that we have implemented, then go over Dash pipeline overview, and then I'll dig into the Intel Dash solution, the overall architecture before implementation and the performance. So what is SONiC Dash, right? Dash stands for Disaggregated API for SONiC hosts. It builds upon SONiC, which is a network operating system. The key idea of Dash is to leverage programmable network hardware, such as the Intel IPU, to provide more efficient networking for cloud as well as data center networking cases. And it is suitable for different use cases, one use case being smart switches. I believe everyone is familiar with smart switches. It's basically combining the intelligence of smart NICs and the complex processing of smart NICs into switches and moving the intelligence to the data center switches rather than the server to keep the complexity low at the server as well as for low cost and power reasons. Some details about Dash implementation. Dash is open source. Its functionality is P4 based. There's a BMP2 reference model available. It enables bidirectional communication between geographically apart VMs. A key tenet of Dash is that it enables stateful connections in the network, along with implementing other advanced features like ACLs, high availability, private link, and service tunneling. So here's a quick overview of the Intel IPU E2100. The key points I would like to note here is if you look on the left side, we have the networking subsystem in which we have the packet processing pipeline. We also call this FXP, which is P4 programmable, and this is where we have implemented the bulk of our Dash pipeline implementation. We also have 16 ARM cores available on the IPU, which help us extend the capability of the packet processing pipeline. So what have we implemented? Basically, Dash, the first milestone it requires is what they call the Baby Hero feature set and scale. In Baby Hero feature set, we implement the VNet to VNet scenario, which includes the outbound routing and inbound routing going out of the VNet and into the VNet. It implements connection tracking with aging, and it implements 5-stage advanced ACL rules as well, along with the underlay forwarding. And this is the scale. And again, the key ones here are the outbound route. It requires 160K outbound routes to be programmed into the network, into the P4 tables, as well as 320K ACL prefixes. The Dash requirement is to support 32 million bidirectional active connections. And there are some testing requirements regarding background flows, which I'll talk about later. So this is the first stage with Baby Hero scale, and then Dash defines Hero scale as well, which will be our next step. So this is an overview of what the SONiC Dash pipeline looks like, right? So as I mentioned before, it is the use case is VNet to VNet, and it is essentially allowing geographically apart VMs to communicate with each other. So what we have in the fast path are, or in both fast and slow path are the ENI and direction lookup. ENI identifies the VM that the packet is either coming from or going to, and then we have direction lookup, which determines whether the packet is inbound or outbound. And that will determine how we apply the ACL policies and routing. Then there's a connection tracking table in which there's a lookup. So if there is a miss, it is considered a slow path packet, which is a new packet of the flow. So it will go through all the ACL policies and overlay routing. And based on the decisions, the connection will be added to the connection tracking table or flow table, as we call it, and then it will be forwarded out. And if there is a hit in the connection tracking table, that means it's an existing flow and it can simply be forwarded. So this basically maps how we have implemented the Dash pipeline onto the Intel IPU. So at the bottom is the networking subsystem, and FXP is the packet processing pipeline that I talked about, and this implements all our P4 tables and functionality like overlay routing and underlay routing hackles as well. And then we have what is shown here as ACC. These are the ARM cores on which we have some packet processing handling, and the flow addition deletion process is handled here as well. And I'll talk more about the data plane in the next slide. But I also want to highlight here the SI API. So we have a custom implementation of the switch abstraction interface, which basically helps us program entries into the P4 tables via the TDI interface. And we use the SciThrift open source API for this. So this is a logical view of the Dash pipeline implementation, right? So in the packet processing pipeline, or in FXP, we have an RX pipeline where we do the ENI and direction lookup. We apply ACLs and routing to new flows. And this is then handled by the ARM cores. All the packets are sent to the ARM cores in order to do the connection tracking, where we have a TCP state machine. We drew any connection updates to the flow tables, as well as aging is handled here as well. And then the packet goes to the TX pipeline, where we do some packet modification, and then the packet is forwarded out. Here are some more details of the P4 pipeline, the P4 RX and TX part that I explained in the previous slide. So we have various match action stages in the FXP pipeline, including exact match, LPM. There's also WCM and hash block, right? So basically the ENI and direction lookup are done in an exact match block, and depending on the direction, the respective ACL policies are applied, which could be inbound or outbound. And these are again 5-stage lookups with Dash requiring 5 network security groups in each direction. That of course we apply outbound routing and inbound routing. So when we add a flow into the flow table for connection tracking purposes, the packet may be coming in outbound direction, but we need to make sure that we have the routing information for both the directions available, so that we can add the flow to the connection tracking table, and it will enable the end-to-end flow in both the directions. So we perform both outbound and inbound routing on an incoming packet. And then we have a hash block which does RSS to map it to the appropriate cores in the ARM cores. And that is where we do the connection update, as I mentioned. And then it goes to the TX pipeline on the right, and the packet is modified and forwarded. And just want to mention that the ACC DPT cap, which runs on the ARM cores, also does flow aging and deletes flows from the flow table when it ages out. So this is our P4 pipeline, and I showed the baby hero scale initially, and we have a deployment which creates the whole baby hero scenario, and we have some performance results from that. The first result shows the max TCP CPS without background flows. What this basically means is we just check how many new connections the IPU can support as we are trying to add more TCP connections into the network. So we use Ixia to generate the traffic, and we use HTTP transactions to basically simulate those TCP connection establishment and tear down. So these are some graphs from Ixia, and we can see that we can achieve a max CPS of about 8.7 million without any packet losses. The next result here is TCP CPS with background flows. So what Dash requires is that we have pre-established background flows, and this is 30 million background flows, 15 million TCP, and 15 million UDP. This also ensures that our flow table is nearly full. The capacity of the flow table that is required by Dash is 32 million active connections. And we add 30 million connections. And then again, you send out TCP CPS traffic into the network, and you see how many CPS connections can be established by the IPU. So in this scenario, since we already have background flows and background traffic flowing for those flows in the network, we are able to achieve a CPS of 3.2 million. And this is with minimum loss 0.001% packet loss. And the requirement for Dash is 3 million CPS. So yeah, this meets those requirements. This next slide shows some throughput numbers, and we have tested this with about 500 byte packet, and we see that the PPS we can achieve in our through the IPU right now is 45 million packets per second, and the corresponding throughput here is 158 gigabits per second for the 200 gig IPU, and this is again 500 byte packet, so it will vary based on the packet size. So here is a summary of our results, which, yeah, again, as I mentioned, 8.7 is our raw TCP CPS throughput, 3.2 million is the CPS with background flows, PPS of 45 million, and then throughput of 158 gigabits per second. So looking ahead, right now we have the flow table implementation in hardware, which provides us a very good CPS and throughput, but it doesn't help us achieve the latency that we desire. So eventually, one of the goals is to move the flow table also to P4 and improve our latency performance. We are also considering P4 DPDK software implementation. Currently, our application on the ARM cores is in C and C++, and P4 DPDK is what we're considering for this pipeline as well. Well, besides that, we'll move to Hero Scale. As I mentioned, we have implemented BB Hero Scale right now, which is much smaller. Hero Scale requires about 100 times more routing entries and then 10 times more ACL entries. So that is our next goal. And then we'll move on to the more advanced features like high availability, SONiC integration, service tunnel, and private link. Right. Well, that's all from me today. Thank you.
I think we have time for a question or two before the break. Anyone? Yeah. Thanks.
Yeah, so good work. So I'm curious about the connection tracking. Why is it on the ARM cores? You couldn't use something like add-on miss, or is that?
Yes, so that's a good question. So our first implementation was using add-on miss in the P4 and also aging. The only challenge is with the Dash scale. Dash requires you to have 32 million bidirectional flows. And in our FXV pipeline in Mount Evans, we currently support 16 million flows with add-on miss and aging. Hence, that is the reason why we moved to software for this, so we could support the scale that Dash is requiring.
Okay, so sorry, you know. Yeah, the other question is, I guess Dash's traffic profiles are very long-lived flows, or how does this? If you had short flows, do you cache every time into the hardware every time from the ARM cores when the flow is established, or?
Yeah, so right now in this existing implementation that we have, we cache all the flows on the ARM cores. That's correct, irrespective of whether they are short-lived or long-lived flows. But yeah, our next steps will include more optimizations, right? So as I mentioned, moving the flow table to hardware, and that may require us to come up with a design where we have partial flows.
I'm trying to understand what's your decision point where you say this has to be put in hardware.
I think Anjali wants to add something here. Go ahead, Anjali.
Yeah, so it's still all the process.
Mhm.
Which is the IPU. You go to the microphone. Yeah, so all the flows are still cached by hardware and they're on DDR. And the DDR is what is shared between the ARM cores and
I see.
the
Okay,
pipe.
so
it's the same.
So the hardware can see the DDR. Okay.
Thanks for the talk. So as we start moving toward more stateful flows and just more stateful things in general on hardware, debuggability becomes a very important issue. This is much more complex than our standard like stateless processing that we do in a lot of P4 devices. And when this type of processing is traditionally done in operating systems, we have debugging tools all the way down to I can stop the code, look at the architectural state of the processor, look at the instructions, look at the registers, and find out exactly what's going on. And as a system operator with this equipment in my network, how do I do that? How do I distinguish between a P4 bug versus a P4 compiler bug versus any other type of bug that might creep into the system that could take down my network?
Well, that's a great question. So so basically we have some internal P4 debugging tools available that we use to debug the pipeline and ensure that we try to make it as bug-free as possible. But we also have APIs available to ensure to basically just check whether what rules are programmed into the hardware, right? So basically you can access information about what flows have been added, and also basically the timer value and everything. We also have counters, and we are planning to add more counters into the pipeline as well, which will also give some idea about where things are going wrong in the pipeline, and that'll throw some light into it as well. We are in the initial stages of this implementation, and this is the first phase, Baby Hero, as we said. So there's a lot more coming, and we'll be adding more enhancements for debugging, and making sure that network administrator can get all the information they require to debug those any issues in the pipeline. Yeah.
Thank you. Just something we would love to see from the operations and system integrator side is open compilers for all this, so we can actually dig all the way down into this and understand how these devices are executing. So thank you.
Yeah, I would just add a little bit more here. From the hardware perspective, one thing that we did right for debuggability is we have all these dynamic counters, so you can associate the counters wherever in the pipe. And that's what we're using for debuggability.
Okay, thanks.
And they're all P4 actions.